In this video, we're going to take a look at exam revision for differentiation. So this video is around first year material for differentiation. So basically kind of like the introduction material for differentiation, differentiation from first principles, stationary points, stuff like that. Okay, so none of the second year material such as chain rule, product rule, quotient rule, anything like that. We do have a separate video for that and I'll leave a link in the description below. So as always, pause the video, have a go at the questions they appear and then double check that your solution matches what we get on the screen. Other than that though, I think that's everything that we need here to get started. So let's begin now with question 1. Starting off with question 1 then, where we have a nice introductory question on differentiation from first principles. So question 1 says, prove from first principles that the derivative of x squared is 2x. So let's just start here by stating the formula then for differentiation from first principles. And don't forget this result is given in the formula book. So this is the limit as h tends to 0 of f of x plus h minus f of x all over h. Okay, so in this case here for this question, f of x, that's the thing that we're looking to differentiate, in this case x squared. So f of x is x squared, and f of x plus h, well, that's going to be x plus h all squared. So x plus h all squared. Okay. We've got everything that we need here then. So now we're looking for the limit as h tends to 0. So f of x plus h, that's x plus h all squared. So x plus h all squared minus f of x, so minus x squared. So minus x squared, and that's all over h. Okay. Then what we need to do is expand these double brackets here. So x plus h times x plus h should hopefully be nice and straightforward. This is the limit as h tends to 0. So I'm going to get x squared here. We have x times h and then h times x. So in total there we've got 2xh or 2hx, whichever way you prefer to write that, plus 2xh. Obviously it doesn't matter. It's multiplication. So 2xh there. We then got h times h, that'd be plus h squared. And then don't forget the minus x squared here. Really easy mistake to make. Just forgetting this minus x squared. So minus x squared. And this is all over h. Okay. Now clearly, x squared and the minus x squared here, they'll cancel. That would be 0. We've then got 2xh plus h squared over h. And what I can do here is cancel through. So 2xh over h, well, the h will cancel there with the h in the denominator. And the same applies here. So h squared over h, that h there, or h squared, that become h to the power of 1. And this h here will cancel, and same again here. So altogether then, I've kind of done that all in one step, but what I get left with then is the limit as h tends to 0 of 2x plus h. So 2x plus h then, what's in a bracket just to make it clear. So now, if we take the limit here, so as h tends to 0, this h here will essentially just disappear. Okay, this essentially just becomes 0. And what we get left with then is 2x. Okay, so that's equal to 2x there as required. And there we have it. So that's the solution there to question 1. Moving on to question 2 now, where we have the curve C with the following equation presented here. Now for the first part A, we want to find two things. We want to find the first derivative and the second derivative. So for the most part, this is a pretty straightforward question to begin with. The only issue that we have here really is the equation and this term here within the equation. So for differentiation, we just go term by term here. So 3x squared, that would be nice and easy. The minus 10, nice and easy. But this 1 over the square root of x, we want to rewrite this here. So 1 over the square root of x. Well, we know that the square root of x is x to the power of a half. So if we have 1 over that, that's going to be x to the power of minus a half. Okay, like so. So now we're just going to rewrite the equation here for the curve C. So y is equal, well, clearly 3x squared and the minus 10 won't change. So 3x squared. 1 over the square root of x, like we said, that is x to the power of minus a half. Like so. And then minus 10. Okay. So now to differentiate this, it's a lot easier than the original equation here. So let's start with part A then. And the first part, we're going to find the first derivative, dy by dx. So dy by dx here, just going term by term. So 3x squared, 3 times 2 is 6, reduce the power by 1. So we get 6x there. X to the power of minus a half. So the coefficient here we don't write, but that is a 1. So 1 times minus a half is minus a half. And then again, we just reduce the power by 1. If our power here is minus a half, if we subtract 1 then, that's the same as minus a half minus 2 over 2. And that gives us minus 3 over 2 there. So minus 3 over 2. And then the minus 10 here, once we differentiate that, well, that's a constant. So if we differentiate that, we get 0. Okay. So there we have it. So that's dy by dx. That's the first derivative. We now also need the second derivative. So remember, to find the second derivative here, we now differentiate the first derivative with respect to x. So for the second derivative, let's just write this down. Like so. Again, we just go term by term. So 6x, if we differentiate this, this would give me 6. And then minus a half x to the power of minus 3 over 2. Well, I've got minus a half times minus 3 over 2. So they're both negative. So the product of those numbers, or those fractions, would be positive. So we get plus. So 1 over 2 times 3 over 2, that would be 3 over 4. We get plus 3 over 4x. And again, we just reduce the power by 1. So minus 3 over 2 minus 1, again, that would be minus 3 over 2 minus 2 over 2, and we get minus 5 over 2 there for the power. Okay, and there we have it. So that's the solution to part A. That's the first derivative and the second derivative. So now let's move on to part B. So for part B, it says find the gradient of the curve when x equals 1. So the gradient of the curve is given by the first derivative. So when x equals 1, all we need to do is substitute that into the first derivative. So when x equals 1, like we said, we're just going to substitute that into the first derivative. And you might find it helpful here just to rewrite the first derivative ever so slightly. So this is equal then to 6x. We can't obviously do anything with that. That's just in its simplest form. Now the minus a half x to the power of minus 3 over 2, we can rewrite that. That's the same as minus 1 over 2x to the power of 3 over 2. Okay, so in that case then, when x equals 1, the first derivative, dy by dx, is going to be equal to 6 times 1. Obviously, that'll be 6, but we'll simplify it in a moment. I just want to keep everything in full detail here, just so you can see the full working. And then minus 1 over 2 lots of 1 to the power of 3 over 2. Well, 1 to the power of 3 over 2, so that's the square root of 1, which is 1. We then cube that, so 1 cubed is 1. So 2 lots of 1 is 2. That's going to be minus 1 over 2, or minus a half there. In that case, then we get 6 minus a half. So 6 minus a half, that is the same as 12 over 2 minus 1 over 2, and that gives us 11 over 2 there. Okay. So the gradient of the curve when x equals 1 is 11 over 2. So that's the solution to part B. Then finally, we have part C here. So for part C, it says, hence or otherwise, find the equation of the tangent at the point where x equals 1, giving your answer in this form here, where a, b, and c are integers to be found. Now, at the point where x equals 1, we already know the value of the gradient. Okay, we found that in part B. So the gradient here is 11 over 2, so we've already got that information. So m is equal to 11 over 2. We have the x coordinate, but what we don't have is the respective y coordinate. So what we need now is the y coordinate when x equals 1. So y is equal. So how do we get the y coordinate? Well, we just go back to the original equation here. Okay, so 3x squared plus 1 over the square root of x minus 10. So that's 3 lots of 1 squared. So 3 lots of 1 squared plus 1 over the square root of 1. And then minus 10. So if we evaluate all of this here, 1 squared is 1. Times it by 3, we get 3. 1 over the square root of 1 is 1. And then minus a 10 here. What I've got is 4 minus 10, and that gives me minus 6 there. Okay. So we've got the x coordinate, we've got the y coordinate. We also know the value of the gradient at this point here. So we now actually have everything that we need here to find the equation of the tangent at that point. So we're going to use the equation of a straight line. We're going to use y minus y1 is equal to m times x minus x1. Okay. And we're going to use the point here of 1 minus 6. Okay. So y minus y1, that's y minus minus 6. That's the same as y plus 6. So y plus 6 is equal to m, which is 11 over 2, times by x minus x1, where x1 is 1. So x minus 1 there. Now, rather than expanding out the right-hand side here, obviously everything would then have a denominator of 2 here on the right-hand side. All I'm going to do straight away is just times through by 2. What that does then is it eliminates this denominator here of 2. Obviously, we want integers here for a, b, and c. So timesing everything through by 2 here, I'm going to get 2 lots of y plus 6. That's going to be 2y plus 12. We get 2y plus 12. And that's going to be equal then to 11x minus, so I've got, well, timing through by the 2, I get rid of this fraction here. So I get 11 lots of x minus 1. So I get 11x minus 11. Just to make that clear. Minus 11 like so. And in this form here, I'm going to keep x positive. So I'm going to take everything over to the right-hand side here. So I've got 11x. We've got this 2y here. So taking that over to the other side, that would be minus 2y. So I've got 11x minus 2y. And then we've got minus 11 minus 12, because that's positive 12 there. So minus 11 minus 12, that gives us minus 23 there. So minus 23, and this is all equal to 0. Okay. And there we have it. So we can now identify the value of a, b, and c. Do that up here. So therefore, a is equal to 11, b is equal to minus 2, and then finally c is equal to minus 23 there. Okay. And there we have it. So that's the solution there to question 2. Moving on to question 3 now, where we have the curve C with the following equation presented here. Now for the first part A, we want to find 2 things. We want to find the first derivative, and we also want to find the second derivative. And before we go on to attempt part A here, we just need to rewrite the equation here for the curve C ever so slightly, because in its current form here, presented as a fraction like this, it's a little bit tricky to differentiate. I mean, if you are familiar with some of the second year materials, such as the quotient rule, then this isn't actually too challenging to differentiate. However, based on first year material only, then this is quite challenging in its current form. So what we need to do is just rewrite it here. So the first thing that I'm going to do is expand the double brackets here in the numerator. So we get y equals, so that would be x squared. I've got 4x and 1x, that's 5x. So I've got x squared plus 5x. And then 1 times 4 is 4. And this is all over x. Okay. And then from here, again, it's still in a fraction. So we just need to go one step further here. So all I'm going to do now is just divide each term here in the numerator by my denominator here of x. So x squared over x, that would be x. 5x over x, that would give me 5. And then finally, 4 over x here. Well, the only thing we can do with that is just write it in index notation. So that would be 4x to the power of minus 1. Okay. And there we have it. So in this form here then, it's a lot easier to differentiate now, just going term by term. So starting off with part A then. So for the first part then, looking for dy by dx. Like we said, we just go term by term here. So nice and straightforward. So if we differentiate x here, that would just give us 1. The 5 here, that's a constant. So when we differentiate that, we get 0. And then 4x to the power of minus 1. Or we do 4 times minus 1, that's minus 4. And then we reduce the power by 1. So if it's 4x to the power of minus 1, we now have 4x to the power of minus 2. Okay, just reducing the power by 1 there. And there we have it. So that's dy by dx. So now we also need the second derivative here. So what I'm going to do now is differentiate dy by dx with respect to x. So for the second derivative, like we said then, just differentiate dy by dx here with respect to x. Well, the 1 here, again, that's a constant. So when we differentiate that, we get 0 again. And then for the minus 4x to the power of minus 2, so differentiating this term here then, we've got minus 4 times minus 2. So that would give me positive 8 there. So we get positive 8. And then x to the power of minus 2, we'll reduce the power by 1. So we get x to the power of minus 3. Okay, so altogether, for the second derivative, we have ax to the power of minus 3. So that's part A done. Now for part B, it says verify that C has a stationary point when x equals 2. Well, we know for stationary points, this occurs when dy by dx equals 0. So for a stationary point, let's just note this here. So for a stationary point, this is when dy by dx equals 0. So if this occurs when x equals 2, hopefully, if we just substitute x equals 2 into the first derivative here, we should get 0. Okay? Now, just to make life a little bit easier here as well, I'm also just going to rewrite the result here for dy by dx. So this is the same then as 1 minus 4 over x squared. So this minus 4x and minus 2, we can write that as 4 over x squared. Okay? So in that case then, when x equals 2, dy by dx is equal to 1 minus 4 over 2 squared. Well, we know that 2 squared is 4. So this is 1 minus 4 over 4, which is the same as 1 minus 1, which is equal to 0 as required. Okay? So therefore, dy by dx is equal to 0 when x equals 2. Okay, so therefore C has a stationary point when x equals 2. So that's part B done. And then finally for part C here, it says using calculus, determine the nature of this stationary point. So when you see a question asking for the nature of a stationary point, it's just asking whether the stationary point is a maximum turning point or a minimum turning point. Okay, so what we need then is the second derivative to determine the nature of the stationary point. And we found that in the first part here. Okay, so the second derivative, we know that's equal then to ax to the power of minus 3. So again, just writing this in a form that's easier to work with when we substitute in our appropriate value. This is the same as a over x cubed, like so. So if we want to determine the nature of this stationary point here, we know this stationary point occurs when x equals 2. So what I need to do then is substitute x equals 2 into the second derivative here to determine the nature of this stationary point. When x equals 2, so when x equals 2 then, the second derivative, this is equal to 8 over 2 cubed. So that's 8 over 8, which is equal to 1. So 8 over 8, which is equal to 1. Now notice here, my second derivative is greater than 0. So this is greater than 0. So therefore, what this means then, if the second derivative is greater than 0, so if it's positive, this means we have a minimum point. So therefore the stationary point is a minimum, I should say minimum turning point, is a minimum, I'll just call it TP, as the second derivative is greater than 0. Okay, and there we have it. So like I said, if you just see anything asking for the nature of the stationary point, straight away you know you need the second derivative. Substitute in the value that you're working with. So like we said, it was x equals 2 from part B, and then just evaluate the second derivative. If it's greater than 0, it's a minimum. If it's less than 0, then it's a maximum. Okay, but there we have it. So in fact, let me just quickly stay here for part B as well. I didn't really mention it here at the very end, but therefore C has a stationary point. So C has a stationary point. Just to be precise, C has a stationary point when x equals 2. Okay. So solution to part A here, dy by dx, second derivative, part B here, and then finally part C here. Let me just box that off as well. Okay. And there we have it. So that's the solution there to question 3. And finally then, if we take a look now at the very last question here, question 4, we have the curve C, which has the following equation presented here. So for the first part, we just want to simply find dy by dx. So we just want to find the first derivative then for part A. Now, to differentiate here, in the current form, it's a little bit tricky to work with if we want to differentiate this. So what we need to do then is find the product then of these 3 brackets here. So what we actually have here is x minus 2 times by itself again, and then we times it by x plus 1. So what we need to do then is expand these triple brackets here. So if I just start by expanding the first 2 brackets here, obviously it doesn't matter which way we expand these, but if I just go from left to right, then we get x squared. I've got minus 2x, and we've got another minus 2x here, so that's minus 4x. And then finally, minus 2 times minus 2 is plus 4. Don't forget the x plus 1 here on the very end. And then if we expand this one step further, so expanding this x plus 1 here with each term on the outside. So x squared times by x is x cubed. We've then got x squared times 1, so that's plus x squared. We've got minus 4x times x, that's minus 4x squared. Minus 4x times 1 is minus 4x. And then finally, we've got 4 times x, which is 4x. And then 4 times 1 is plus 4. Okay. And all I want to do here then is just simplify and collect like terms. So minus 4x plus 4x, I can see straight away they'll just cancel. And at that point, then we're pretty much done here. So it's collecting like terms now. Obviously, I can't do anything with the x cubed, so I'll just be as it is. X cubed. I've got x squared minus 4x squared, so that's going to be minus 3x squared. Minus 3x squared there. And then we simply got plus 4 at the very end. Okay. So now we can easily find dy by dx, just going term by term here. So for part A then, going term by term for dy by dx. So if I've got x cubed here, that's going to be 1 times by 3, reduce the power by 1, so we get 3x squared there. I've got 3x squared. Minus 3 times 2 is minus 6, reduce the power by 1, so we get minus 6x. And then the 4 here, well, that's a constant, so when we differentiate that, we get 0. Okay, so there we have it. So that's simply the solution to part A. That's the first derivative there, dy by dx. So now let's move on to part B. So part B says, hence or otherwise find the coordinates of the curve's local maximum. So if we're looking for the coordinates of the curve's local maximum, we need dy by dx to be equal to 0. Okay, so we need dy by dx to be equal to 0. Okay, So dy by dx is equal to 3x squared minus 6x. So if we set that equal to 0, we get 3x squared minus 6x equals 0. So here we factorize. I get 3x on the outside. Then inside the bracket, we get x minus 2. And this is equal to 0. So from here, we get two solutions. I get x equals 0. And I get x equals 2. Okay. So in this case here then, we now need to know which of these 2 points, so when x equals 0 and when x equals 2, which one would give the maximum and which would give the minimum. So to do that, we also need the second derivative. So let's find the second derivative over here. So for the second derivative then, we just differentiate dy by dx with respect to x. So 3 times 2 is 6, reduce the power by 1. So we get 6x there. And then minus 6x, if we differentiate that, we get minus 6 there. Okay. Now we're looking for the coordinates of the curve's local maximum. So like we said, we've got these 2 points here, x equals 0 and x equals 2. So one of these will be the local maximum and one will be the local minimum. And like we said, we found the second derivative then to determine the nature of these 2 points. So we're going to substitute both of these points in, but clearly what I can see straight away just by inspection here is if I substitute x equals 0 into this here, so if x equals 0, then the second derivative would be equal to 6 times 0, which is 0 minus 6. So the second derivative then is equal to minus 6, which is less than 0. So that means we have the maximum point there, okay, or the maximum turning point. So the correct point then would be x equals 0. That's the one that we want here, okay? So just highlight that here. That's one we're looking for. So let me just make a note of that here then. So the second derivative is equal to minus 6, which is less than 0. So therefore, we have the local maximum. Okay. So in that case now, we're just looking for the coordinates of the curve's local maximum. Well, we have the x coordinate. All we simply need then is the y coordinate. Okay. So when x equals 0, all we're going to simply do here then is substitute x equals 0 into the equation here for y. So y is equal then, it's going to be 0 minus 2 all squared. And then we times this here by 0 plus 1. So this is going to be minus 2 squared. And then we times that by 1. Well, minus 2 squared, that's 4. Minus 2 times minus 2 is 4. Times that by 1, and we get 4 there. Okay, so the coordinates of the curve's local maximum. So the local maximum is given as, or the coordinates of the local maximum are given as, so our x coordinate is 0, and our y coordinate is 4. Okay. And there we have it. So that's the solution to B. That was the solution to A, and that gives the solution there to the very last question, question 4. And that actually brings us to the end of this video on exam revision for differentiation.